We went over this yesterday, but I'd like to thank again for this kind invitation. I'm very happy to be here, so it's a privilege to be here back in Sevilla with this group. So thanks for the invitation.
So what I'd like to talk about today is, again, related to the use of phasor measurements, but
this is somewhat of a different application. In fact, it's sort of like applications which are sort of fitted into an existing solution. So we are sort of looking backwards. I'll first present the solution or the generic problem and then show that this fits into two applications which are somewhat unrelated, even though we can apply the same technique to both of these problems solutions. So again, we went over this yesterday, but those of you who were not here, just some greetings from Northeastern. In case you don't know where it is, it's in the northeastern part of, as you can imagine from the title, northeastern part of the U.S. in Boston. And it's roughly 16,000 undergrads and 5,000 graduate students. That's sort of a size of a school. And we do have computer and College of Computers and College of Engineering. And our department is under College of Engineering. And we have a bunch of faculty working in different areas of ECE. And of course, I'm with the power group. So the outline of the talk today. So I'd like to talk a bit about phasor measurement units. So this might be part of it, maybe a bit repetition from yesterday in case some of you are not here. So I'd like to go over that. But then after that, I'd like to talk about two problems. One is the external network model error identification, and the other one is the fault location or fault detection. These are sort of classical problems in power systems. And it turns out that these two problems fit into the same sort of formulation, which we can use the same type of solution. And then we'll have some closing remarks. So, so this is part of the repetition, phasor measurement units. Those of you who are not too familiar with this, they were introduced in late 80s. The concept was already around, but the actual device prototype was introduced by Professors Fatke and Thorpe. And it's basically a device which uses GPS synchronization to come up with synchronized measurements at remote locations in the system. So, and then the device looks like this. The inputs are coming from instrument transformers. The samples are tagged by a clock, GPS clock, so they are accurately tagged, and with tagged signals, you collect them in a phasor data concentrator where they are aligned. So this aligned data is then provided for applications, either in a corporate or a regional setting. So this is the sort of picture. We don't really have a reference. The reference happens to be the GPS. So you basically come up with a bunch of phasors which are implicitly assumed to be referenced with respect to this GPS. We typically use, of course, we monitor all three phases, but then we convert them into positive sequence, and we actually only receive the positive sequence signals, voltages and currents from PMUs, phasor measurement units. So these are some of the details of how we receive this data, synchronized data. So what do we do with that? So before we do that, I'd like to present this very generic problem. And it's the good old problem of underdetermined set of equations. If you have a set of equations, like you have 1,000 unknowns and just 3 equations, obviously you cannot solve them for 1,000 infinite solutions. So normally we say that this has no solution, or it has infinite number of solutions. But if you add this additional information that before solving it, we already know the structure of the solution. In other words, we already know that this X is such that only few, say K, out of N of these entries are non-zero. Of course, we don't know which ones and we don't know what those values are. But if we already know that very few of these entries will be non-zero and the rest of the entries will be zero, then there are ways of actually solving for this X, even though you have so few equations and so many unknowns. So this is a classical problem, and there have been developments towards solving this sort of problem in an efficient and reliable, robust fashion. So, looking at those solutions and looking at this sort of problem, you can also say, okay, do we have such problems in power systems, and can we solve these problems using some of these existing solutions, and perhaps also taking advantage of phasor measurements. So that's basically what this talk is about. And I'd like to show you two examples of that. One is this line outage detection, or the external network model error detection. And the other one is the fault detection or fault location. Now, the first problem, obviously, those of you who mingled with this sort of problem, you might know that there are very few equations because you're essentially looking at the external system, but you are observing what's going on from very few points, typically at the boundary. So you have very few equations to work with, but you have a large number of candidate lines in the external system, which may be out of in service. And of course, we know that, or the problem we assume to be is that one of these lines is disconnected, and we are trying to figure out which one. The other problem, fault detection problem, is again, if you set it up in such a way that you don't have a sensor at the terminal of each and every line, but you have a few, maybe a small percentage of the buses have sensors, then essentially you'll have few equations to write based on these sensors, and a large number of candidate branches, and you know that one of these branches is faulted. And then there's an additional complication. You not only need to know which branch is faulted, but you need to exactly find the location of that fault along that branch, which is somewhat of an additional complication. Additional logic is needed in addition to this sort of problem. So these are the two examples I'd like to look at. So let's start with the first one, the line outage detection problem. So the problem is simply stated like this: detect, identify line switching in the external system by monitoring only your internal system. And the internal system essentially assumes that you have real-time internal system state, because you have the state estimator. You have the real-time internal topology, so hopefully you know what your connections are in your internal system. And then we also assume that there is a base case external state, and the base case external topology, they are available. So initially, we assume that we do have full knowledge about the whole system, including internal and external, but eventually, as time progresses, of course, we'll have access to the internal system state and topology, but the external system state and topology may not be available to us in real time. So we are trying to sort of track changes in the external system based on what we know in the internal system. But specifically, we are looking at detecting an outage of a line in the external system based on what we know about the internal system. So this is fairly well-known equivalence. So if there is a line in the external system which is connected like this, and then it gets disconnected. So if these circuit breakers open and it gets disconnected, therefore this line flow will be zero. You can take this and replace it by an equivalent picture where this is still connected, but by adding appropriate injections here on each side, which are equal to this flow, you can eliminate that flow and make this picture look like exactly that picture in terms of everything, voltages, these flows, and so forth, other than these three artificially inserted flows. And the nice thing about this is, of course,
this eliminates the topology change. In other words, we can still keep this model here.
And what we are trying to do is emulate this outage without the actual outage, but by including these injections. So this equivalence can help us in identifying an external line branch outage, because if you think about it, essentially a line outage will be equivalent to a change of a pair of injections at the terminals of this outaged branch. So the branch remains closed, but you notice this jump in the injections at the terminals. So that the problem turns into identifying these jumps in the injections rather than a change in the topology. So if you present the problem like that, then you can certainly, well, let's start with the linear approximation. If you take the linear approximation of the equations representing the whole system, internal and external, you can write it out like this. This is the linear approximation, B being the susceptance, I mean the Y, the imaginary part of Y bus, and we get rid of the reactive part, so it's the real part, real power versus theta linearized version of the equations. And then you can partition it like this, where here we are assuming that the external system is 2 subscript 2, and then internal system is subscript 1. So that way you can partition the equations like this. And I'm also including some errors here because this is a linearization, and there may be errors associated with this, obviously. So again, using this equivalence, what we are trying to figure out is this pair, and in the linearized version, since there are no losses, these will be identical except for their signs at the two ends of the outaged branch. So the problem looks something like this. So you have this base case equation. So these are the internal external injections all together inserted in this vector P0, and this is the base case solution theta 0. And then we introduce this change, this outage, and that will look more like this, as you can see here. If it's a single line connecting K to M, if you look at the admittance matrix, essentially you will see changes in these 4 locations. So delta B is a very, very sparse matrix. And with this change, of course, we are assuming that the injections are remaining the same. So the loads, injection, and generation remain the same. So with these injections remaining the same, you get a different answer now, which is theta 1. But then you can take this and throw it to the right-hand side and call this product delta P. And the equation becomes B times theta 1 equals P0 minus this product, which I called delta P. So, so based on this structure, you can show easily that the structure of delta P will be a sparse injection vector, which will look like this, all zeros except for 2 entries, and those 2 entries corresponding to bus K and M, or row K and M. And of course, their signs will be opposite because of these signs here. So, so the equation will be this, and you can see that we are keeping the same topology, so B remains the same. Of course, the solution changes to the post-outage system state, and the injection, of course, changes as well. So, so the question is, if we are not observing the entire theta 1, we are only observing the ones corresponding to our internal system. And of course, the same thing is true for the external system. We are not observing the changes in the external system injections. So if we are just observing the internal system state, can we actually solve for these unknowns which are happening in the external system? So, so we can rewrite this equation and then reduce it by eliminating this unknown delta theta 2, which is the state of the external system. We eliminate that by this kind of reduction, and we come up with this equation. So here you can see that I'm reducing, this is the Cron reduction of that, and I'm keeping delta theta 1 as my variable, and then delta P1, and then here we have the injections in the external system. Again, through the Cron reduction, you get this multiplier here on the right-hand side, and then these are the errors, and we can lump them into one error vector. So you get this equation, and this equation, the left-hand side here is, or can be known, because these relate to the internal system variables, the state and the injections. And then the external system, of course, we don't know. So delta P2 is the unknown. But we know that this unknown, in case of this line outage, will look like this. All zeros except for these two entries. So the problem then becomes this: a constant matrix, a constant array, which is the right-hand side array, and then these equations, these terms in the equation where this represents our unknown delta P2, and these are the error terms. Notice that because of the structure, this matrix, which is the off-diagonal matrix of the admittance matrix, is quite sparse. Actually, it's almost empty because it will have zeros corresponding to the rows of the internal buses, and there will be only non-zeros along the rows of those corresponding to the boundaries. So this actually, even though it looks like a big matrix, it actually boils down to a very few equations, and those are the ones corresponding to the boundaries of your internal system, connecting it to the external system. So the structure will look something like this. I'm skipping these details, but essentially you will have one matrix here, which is a rectangular matrix like this, with few rows and many columns. And those many columns correspond to this unknown delta P2, which we know is long but empty. There are only two non-zeros in it. And then, of course, this right-hand side, or the left-hand side in this case, is known because it's all internal variables and injections. So, so the problem looks something like this. Now, the only thing is we not only not know which ones are non-zero, we also not know the value, this P value, or the flow, or this pair of injections representing the outage. So this becomes a sparse equation, except the fact that we have it's not a binary equation, so there are plus ones and minus ones and zeros. So we turn this into a binary form by expanding it, and this is the usual common trick used in linear programming also. So we sort of double the dimension to get rid of this -1 and turn everything into positive ones. So then the unknown vector becomes a binary vector, strictly 0 and 1. And then, of course, the dimension grows a bit. So we get this larger matrix, coefficient matrix. But in any case, we get this binary conversion, and then we can write an optimization we can formulate an optimization problem like this. Then it's a binary problem. We put a constraint here. As you can see, we are saying that only two entries in X should be non-zero, not only non-zero, but 1. So they should add up to 2. So with this constraint and this non-negativity constraints, you set up this problem. and solve it, and you get a solution. Now, obviously, the solution will not be entirely correct because we have been using the linearized model, which ignores the losses. So if you introduce the AC model with losses, the two ends of these two pairs of injections will be different because of the loss along the line. So these two entries will not be P and minus P, but they will be different. And not only that, since it's an AC problem, we'll get additional errors. So these numbers will not be entirely zero. They will be small compared to these numbers there. So we have to accommodate for those things. So we reformulate it with losses. We put some limits to ensure that these are more significant compared to these others. And then we also change our formulation and add more variables to take into account the fact that this non-zero and that non-zero are not exactly equal in absolute value. So those are given here. So those details are not that important, but in the end, you can solve it. And yeah, so here, this is an example of how you can actually do it for a small system. So you break the system up here, and you call this part internal, call that part external, and then you look at an outage here, and so it's a two-zone problem, so essentially you are looking at 4 boundary buses from which you are observing the external system, and those buses are connecting to all these external system boundaries, and this is the external system. So essentially you have four equations in the end to be able to detect several branch outages here, because you have connections from these 4 points to the external system. So that V12, that submatrix, has only 4 equations to work with. So if you apply this and use the DC approximate model with no load changes, we get results here, which, it's just a verification that it's actually working. These are the outage lines, and then it goes and finds this plus and minus 1 points at the terminals of these lines for each case. And this shows the pre-outage flow on the removed line to show that, they are small flows, large flows, these different cases here. So, but in this case, we are assuming that the load is not changing at all. So from one instant to the next, when you are looking at these changes, you assume that injections are fixed completely, which is not realistic because, the system is moving along as you do these things. So, and also, of course, this is also the DC approximation. So, so then we look at the case where we take into account losses, not the DC approximation. And here are some results. Again, in this case, we have 2 separate variables. One variable is the P, which is the flow along the line. The other one is the Q, and that's the difference between the 2 injections. In other words, if one is P, the other one will be P plus Q. And you notice that these are small compared to P. So if one is 3.5, the other one will be 3.56 plus this and so forth. So so these numbers here represent those small loss additions due to this formulation, and you can see that it's the same thing. It just allocates these to the terminal buses. And then now, if you further go and introduce slowly changing loads or generation, which is the more realistic case in an actual setting, then you also see errors. So here we notice that in addition to these, we also get errors because the remaining variables in X are not going to be exactly 0 because there are some load changes. Therefore, you see these small changes in injections in every bus. But those injections we assume to be small compared to the outage line. So that means it immediately shows you the limitation of the technique, which means if you have a very lightly loaded line and the line is taken out, since the light load may be in the same order as this load change, slow load change, you may not be able to differentiate whether it's actually a load change or a line outage. So there is that limitation for the lightly loaded lines. But then again, you might say, okay, if lightly loaded line is taken out, maybe it has a small impact on the contingency analysis, which is why you need the external network equivalent, so forth. So I think that was my last slide. Yeah. So this is the first problem, and you notice that we used binary programming, integer programming, to solve it, and then we also did all sorts of formulation tricks here to take into account losses and the fact that there is load changes and so forth. Now, when it comes to the second problem, it's slightly different in the sense that it's the fault location problem, and just simply stated, fault location problem is determine the faulted line or the line segment, and once you do that, you also determine the distance between one of the line terminals to the actual fault location. So that way, you determine the faulted line as well as the location of the fault along that branch, suspected branch. So this is the fault location problem. And as you know, probably most of you also worked on this. There are many different ways to do this. Over the years, we have seen millions of papers on fault location. So there is this category of papers on fault location using power frequency, or they are sometimes referred as impedance-based methods. So they basically filter out high frequency and then they estimate the impedance to fault. The others are using high frequency or traveling waves, and they either capture the wavefronts or they use high frequency sampling to do other correlation studies. And then finally, there are all these techniques which use pattern recognition, intelligent methods, and so forth. So this is another category. So there is a huge literature on this. So I'm just skipping all that by, realizing that and appreciating the work. But since this is not directly linked to any of these, I'm skipping that. And I'm just going to present the basic motivation for this. So the basic motivation is the observation that if you have a fault, as you know, you can model the fault by an injected current here. Say if the fault is here, you can model the fault by an injected current. And this injected current, which is a negative current actually, will of course change the solution. And so the voltages will go from the pre-fault values, Vk and Vm, to the post-fault values, which are this plus delta Vk and that plus delta Vm. So that's the picture. So this is the pre-fault in black and post-fault in black and red. Now, you can show that instead of applying a fault and injecting a current here, you can do similarly what we did for the line outage. You can use two injections, one here, another there, so that these two injections will give you the same voltage changes. So you get the same voltage change here and there, but instead of using a single IF, you use two injections at the two ends. So the nice thing here is, even though we don't know where the fault is, we know the terminal, so we know exactly where to inject these currents, of course, provided that we know what IF is, and we don't initially. Okay, so there's this equivalence. But in addition to this equivalence, you can also show that there's another interesting property, which is that when you find these equivalent injections, I'm sorry about this, there should be an I2 here, and this should be I3. Somehow it's missing here. So this is I2 and this is I3. So in addition to that, you can show that these two add up to the equivalent fault current. And not only that, the ratio of I2 to I3, so the ratio of this to that, will be the ratio of this branch impedance to fault to this branch impedance to fault from the two ends. So in other words, if you can somehow figure out what these are, then you can also figure out the location of the fault. And interesting enough, this not only works for two terminals, irrespective of the shunts, it not only works for two terminals, but it also works for three terminals. So if you have three terminal lines, you can also devise another equivalent relation where you can show that knowing these three terminal injections, you can find the location of the fault, whether it's on this or that or this, one of the three. So that's basically the main motivation of this formulation. So then the question is, can line faults be detected, located using sparse set of phasor measurements? In other words, instead of measuring all the bus voltages in the system, which may not be possible now because we don't have that many phasor measurements, can we use very few phasor measurements in the system and detect and locate faults? Can we do it for any type of fault in a three-phase system, like line to line, line to ground, so forth? And then if we can, what are the limitations? How do we place these phasor measurements so that there are enough of them at the right locations, which will allow this to happen? So these are the questions after the motivating example. So I'd like to show you this just to maybe clarify, in case it wasn't so far, what I mean by the motivating formulation. So as you know, in the US, unlike here, the distribution systems are sometimes, not sometimes, and most of the time, they contain mixed number of phases. Like it may start, the distribution system may start as a three-phase system, and then eventually it may become a single phase or a two-phase feeder, and then finally a single-phase feeder. So you may see along the same feeder, three-phase, two-phase, single-phase sections. So this is an example where this is the case. So you have this, as you can tell from the picture, this is an ATP model. So it's a three-phase feeder, and then there are single-phase and two-phase feeders here. And what we did is we applied a fault along this branch 2 to 5, which is a three-phase branch, and applied a two-phase, double phase to ground, double line to ground fault along this branch about a third of the distance of the entire branch from the line terminal N2. And it's a line to ground to fault, line to line to ground to fault. So you expect, if you want to model this as a pair of injections, obviously it's a three-phase system, so you will need two injections in phase A and B on one end, and then two injections at phase A and B at the other end, so that the equivalence that we talked about here will work. This will work. So in this case, you can see that what we did is we actually applied the fault. We obtained the solution. Delta V jumps. The voltages jump in every bus. We got the solution. So then, using the solution, we injected it back into the admittance equation to obtain the corresponding changes in the injections. And this is what we got. You can see that all the injections are zero at all these buses, or nodes, actually. These are three-phase nodes. So this these represent phase A, B, C, or just A, B, or C, depending on whether it's 3-phase, 2-phase, or single-phase. So these are the actual node injections. They're all zeros except those 4. And those 4 are the ones corresponding to phase AB and phase AB at the 2 ends of this line 2 to 5. And more interestingly, if you look at the ratio of this to that, it's roughly, I don't know if you can tell, but this is 1500, this is 500. So the ratio is 1 to 3 because of this distance of the actual fault from this end is 1/3 of this line length of 2 to 5. So this sort of verifies, this is really just nothing. It just verifies for this example that even for this mixed number of phases, a fault which is unbalanced, double phase to ground, it works. So this verifies the equivalence. So, okay, so coming back to the problem, so you can now think about the system like this as a large system, and you have a set of buses, and not all buses are equipped with PMUs. So we are assuming that we have measured buses, the buses where we have PMUs. So these green ones have PMUs, and the red ones are not measured. They don't have any equipment, any sensors there. So with this kind of picture, you can, again, write an equation, the linear equation for the network equations here, voltages, currents, admittance matrix. U stands for unmeasured, M stands for measured, so you can partition it with respect to unmeasured and measured buses, and you can see here that we have unmeasured bus voltages which we don't want, so you can eliminate it again using the Cron reduction. So you can come up with this equation where this is gone, this unknown current is on the right-hand side. This is the measured current, this is the measured voltage, and we can take this and call this product T as a coefficient matrix, move it out here, and then create a right-hand side which includes this, which we can calculate because VM is measured, and of course that is also, so the right-hand side can be measured, and the left-hand side has a known coefficient matrix and an unknown current. Now, this unknown current is sparse. We know it's sparse because of the formulation, right? So, and then, of course, we don't like complex numbers as before, so I switched this formulation from complex to real. That's basically what we are doing here. So, but the equation remains in the same structure now. The unknowns are betas, and again, we have a sparse beta. And now, instead of using the previous integer programming approach, by this time we were educated a bit more, so we found other more recent techniques of doing this, one of which is coming from this reference. It's a very nice way of solving that problem in a very sort of efficient way. It's referred in the literature as Lars algorithm. So we set up a problem. This is the equation. So we know this, we know we can build that, and this is the sparse unknown vector that we are after. So you can build an optimization problem like this, and you notice that it's actually like the L2 norm minimization, but with a penalty which penalizes the solution L1 norm with a multiplier lambda here. So lambda is sort of a tuning parameter in this case. Okay, so before we solve that, we should also, we are concerned about whether this is unique or not. In other words, going back to this, is this solution unique? Can we rely, even if we get the solution, can we rely on that solution or not? So to find that, again, we refer to the literature, and there are some results on this, which translates into the power system or the fault location problem like this. Essentially, uniqueness condition translates into finding the rank of this matrix T this matrix T corresponding to the terminals, corresponding to the buses, which represent the terminals of this faulted line, and making sure that this set of GIs, this set of columns in T corresponding to these terminals, give you a full rank. Indeed, if that's not the case, that's one way to go back and change your sensor configuration. So that also helps you to do sensor placement. This is what we did by using that logic. We created a measurement placement logic. So essentially, it checks this T matrix columns corresponding to these terminals. And if it runs into issues of
linear dependence, then it beefs up the measurement. In other words, it keeps adding sensors.
And then there's some logic in the way we add the sensors. The terminals with more connections to the measurement set are the ones which are favored initially in this. So there's this sort of logic. We place sensors. And the end result is something like this. For instance, if you look at a system with 118 buses, and this is actually a positive sequence model, but we applied it anyway. And then we also checked it with a three-phase system later. So for the positive sequence model, the placement ended up placing 41 voltage phasor measurements. And with these, as you can imagine, some of these voltage phasors may be placed at locations where they represent terminals of a given line. So in that case, there's no need to use this, because if you have the terminal voltages, you can immediately find the solution. So because of that, you don't have to create all fault cases, all branch faults. And the ones that were needed were only 131 out of, I think, 178 branches or something. So with those, we run this, and for the noise-free case, you can see that the average error was almost zero. So this was pretty reliable in this case. On the other hand, as you keep adding noise to the measurements, the performance got worse. The number of iterations grew, the required number of iterations to converge, and then the error, and this is the average error of injections, meaning how many times we hit the right injections as the solution, how many times we got, like in this case, we got probably 20% of the times we got the wrong injections as you keep increasing the noise in this way. So it's not insensitive to noise, to say it sort of in another way of explaining. It's sensitive to noise, and if the noise in the measurements grows, then your success rate drops. And we tried it also for the three-phase model, which is this. We take the 30-bus system and turned it into a three-phase equivalent system, and we applied all sorts of different types of faults with 16 voltage phasor measurements in this case, and we got similar results. Again, here the number of iterations grow with noise, and the success rate drops. Actually, this is not too bad, even though it looks worse than the previous one, but this is a small number. But yet, still we see this increase of drop in performance as you increase the noise. We have some more results on this, which I was unable to include here because they were recent. And the results are mainly extension of this to 3-terminal lines, not only 2 terminals, but 3-terminal lines. And also there are some now new methods of dealing with this noise issue and making it less sensitive to noise. So that's what I mean by this, but some of this work is done also now. and then the same thing goes for that. I think the bottom line is the PMUs can be used to track network changes in the line, in the external system as line outages, or again, network, if you consider them as network changes, you can track faults and also locate them along that faulted line without the need for measuring each and every bus or even having a fully observable network in the state estimation sense. Because if you look at what we have as sensors, as measurements in these examples, actually we don't have an observable network. So if you take those measurements and try to estimate the state of the system, you can't. They are unobservable. Okay, so I'd like to credit my students who worked on these two projects and thank you for listening. So I'll try to answer questions if you have.
Okay, thank you very much, Ali. I have here the microphone, trying to switch it on so that you can make questions. So it's okay, it's on. So any question on the floor? Here in the room, and then afterwards I will give chance for remote people to make questions.
Regarding the problem of detection of outage in a line, I'm assuming that there is no company that can call you and tell you that there is a line in their area, and they can tell you the line and the features of the line. Is
Right. So we are assuming that there is that missing information. It's probably less of an issue if you have, this may be an unreported outage even for the company, your neighboring company. I mean, they may not also detect it, or it may be detected with a delay. So because this is sort of almost online, because we are measuring these things online. So you may know about it before even you are told by the others with a delay. So, but yes, absolutely. We assume that you don't know about it through the neighbors. Yeah.
Don't be shy. Question?
Hello. You were talking about internal and external systems, and I want to know what is the interest for an internal system to know what line was taken out?
Yes. So I think, that's a good question. Mainly, as you know, the way systems operate, the control centers, they run the so-called contingency analysis on a regular basis. So at each point in time, you have to sort of look ahead about an hour and look at how these things, loads and so forth, are changing. And then you go through power flow solutions corresponding to a bunch of contingencies like line outages, generation losses, so forth. And make sure that under those contingencies, your system remains safe, secure. And if it's not secure, you run some sort of optimization to dispatch your generation so that you make it secure against these contingencies. So to run all this, you need a power flow, right? So to run that power flow, you need the right external system model, because if you don't have that model, what you get will be the wrong solution. So you need to keep, if not perfect, but at least approximately good external system model to do the contingency analysis.
More questions? Okay, to give time to the other people around, outside Seville, which a delay of about almost 1 minute, I have a couple of questions. I'm curious about. In the first problem you were dealing with, you began with the DC low flow model, and then you tried to afterwards to improve the accuracy of the model by adding losses, active power losses. So I wonder why have not you tried to directly use like in the second part, the meet and the complex phasor and the complex everything, and the detailed linear model, because you are having a phasor which relate linearly with the currents and the metis and the like. So the linear circuit model could be probably provide more accuracy than the DC. I mean, the angles, only the angles, like
right.
So
right. So well, the reason was, that's a good question. The reason was initially we didn't start looking at the problem assuming having phasor measurements
because
typically you don't have that many phasor measurements in the system. So we started out by looking at it as a conventional, SCADA-based solution. Can we do something about it just using SCADA? And then
power.
We realized that we can also improve it by adding phasor measurements. But that will work with or without phasor measurements. With phasor measurements, I think it will be more reliable, more robust, maybe. But you might. There's an extension to it where, like, if you have sort of a sparsely located PMU measurements which you have access through the PDC from your neighbors. So in the external system, you have these sparsely located phasor measurements. You can always bring them in and designate them as your internal buses in the reduction model. So you can keep them in the internal system. So it will be a sort of an artificial internal system with all these buses included. So that might also create sort of a virtual internal system for you where you use those as information. And that also adds to the information, even though they are not in your internal system or the boundaries. So the reason why we don't have what you suggested was because initially we started out by SCADA and then we sort of gradually added on PMUs. But what you are saying is obviously correct. I mean, you can do it right.
Yeah, I'm aware of a couple of papers by these guys from Illinois, Overby.
Yes.
The first one dealing with, they were pioneers in this idea, a single line outages, but there's another one, probably a conference paper, I don't know, dealing with double line outages. And they were using the active power phase angle DC low flow model. So have you tried also double line outages? And another question is, what is the main difference between your work and theirs?
I think their work is more of a, they don't use this sparse estimation. I think they are more of a matching. They are matching the signatures. Whereas here, this is strictly sparse estimation. You put it in the optimization problem, it gives you the solution.
I think Yanaki has another contribution in this regard, right? So, but philosophically, I think this idea of using information from the external system is a radical change in the way the operators are dealing nowadays. For instance, in Europe, I don't imagine in the Spanish operator, for instance, having information in real time, PMUs from their networks, from France or Portugal. Well, Portugal may be because they are linked in the same market, but France, for instance, is I don't know if they will be willing to share this information with the neighbor. Probably they will be only exchanging information of tie lines and most border buses. So, but it could be nice for them to have this information. So this is
this PDC. I mean, the way it's set up right now in the US, I think it's right now people are sharing. As far as I know, there are some companies who are sharing each other's PMU information.
Mm-hmm.
So this is, but of course it's not, they are states, they are not countries. So maybe it's a different story between countries. So Depends on the setting.
Yeah.
Maybe.
Okay, regarding the second part, there is no question. I will give you the opportunity to make more questions afterwards. Regarding the second part, which I believe is more challenging, more interesting probably, and more difficult, I wonder if you are thinking of distribution of transmission system, because the example you have given, 118 bus and 30 bus, are transmission system, meshed transmission system, whereas at the beginning you were using an example of a signature, of this, with this radial unbalanced distribution system, right? So what is the environment where you are thinking about? Is distribution or transmission? Because then I have more questions depending on your answer.
Yeah. No, I think there is no, we didn't differentiate. It's just the fact that it works, whether it's single phase or multi-phase or mixed phase or all three phase, it doesn't matter. It works. The only thing is, if it's a radial system, the placement of sensors may be an issue, because you don't have that luxury of reaching out from different paths to that point. So you have only one path.
Okay, yeah. My question was because what I find really useful and interesting is in distribution case, because at the transmission system, as you know, they have these digital relays, IEDs.
Yes.
And those digital relays, most of them, for instance, Red Electrica is adding PMUs just for relaying purposes, not for state estimation. So those IEDs can be immediately connected, can report the trigger of the line immediately to the control center. So they could do basically the same. So in transmission system, there are other sources of information, mainly the protected system. Right. So they can give you this information readily, almost real time, without alarm, and giving you all an estimation of the distance, because they are distant relays, so they can give you. But the real challenge is to have the same information, luxury of information in the distribution. But the question is, do we have phasor measurement in distribution system? I don't know.
Yeah.
I don't know.
Yeah.
At least in Spain, we don't have PMUs at the distribution system yet. I'm not aware of. So, but maybe in the USA, some companies have already put, because there is now a wave of new papers trying to argue that we will have also PMUs at the distribution system. So this may be the case if they are very cheap.
Yeah, there is, of course, resistance in the sense that you don't really need, at least right now, frequency information in the distribution system. So, and if you are using PMUs, like they do it for some transmission applications, mainly for frequency monitoring, then it's probably not useful and not justifiable. But if you can come up with applications like this or others, and people may start getting motivated to deploy PMUs in distribution.
Mm-hmm.
So maybe in the long run, we will see PMUs.
Yeah, the idea, my reflection is in this saying is that we already have a lot of protected relays, which are now digital and can communicate quickly with the control center. As quickly as PMUs. So, but we are now adding PMUs for several reasons to synchronize the relays and the distant relays and the pilot relay and this kind of thing. And we are now trying to take advantage of this information provided by PMUs for other purposes, like, estimating the parameters of a generator or whatever. Yeah. And I don't know whether this, we are duplicating efforts, we are having different and coordinated ways of reaching the same conclusion. Probably you added the information provided by relays in this model could be more accurate or something. I don't know. Yeah,
could be. On the other hand, if you consider, at least for the time being, the infrastructure supporting SCADA. I don't know about relaying, but SCADA versus the infrastructure supporting the phasor measurements, they are not the same. So in other words, there may be situations where a storm may come through and you may lose SCADA, but you may not lose PMU connectivity. So in that case, this may be just a complementary solution to such cases.
If they're using different channels, yeah. Okay. Any question now? Any questions here? And if there are several connections from outside, there are 5 or 6. ¿Cuántas conexiones, Antonio? How many? Having today a maximum of 8 people, 8 connections to the YouTube channel, but none of them are probably today available to make questions. So there are no questions from remote. Any question local in the room? No? Okay, thank you very much for such an interesting
you.
discussion.
Thanks.